All right, so I'm going to briefly talk about the difference between the Harvard and von Neumann architectures, and then I'm going to look at some past paper questions. In this article, link below, there's one on specifically on Harvard and von Neumann differences, but in the main one about CPUs, there's lots of past paper questions. One of the first questions it asks is describe a feature that's not part of the standard von Neumann architecture. So to know what that means, you kind of need to know what's in the standard von Neumann architecture and what isn't. And it's important to know the difference between Harvard architecture and von Neumann, because sometimes they do ask you questions about that. So here's a picture. On the left is von Neumann, on the right is Harvard. The main difference is that Harvard has two stores, one for the program data or instructions, and one just for the data. And so two sets of buses going in and out, whereas the von Neumann machine is simpler and has just one memory where it stores data and instructions. So the problems that comes up with for von Neumann is that you may have situations where you have bottlenecks, and that slows down processing of information, whereas the Harvard machine will be much faster because it won't get those bottleneck issues. That's one of the main differences. The other one is pipelining. So the Harvard architecture traditionally can do fetch, execute, and decode several different instructions at the same time. So whilst it's fetching, it can be executing the previous one it just fetched, and it can be decoding the previous one it just fetched, and it could be executing the one it's just decoded. And so it's kind of like very efficient. But problems and reasons why von Neumann architecture is in most modern day PCs is because of its simplicity and cost. So as a Harvard machine was more superior perhaps, but the complexity of it in terms of programming it and adding to it, updating it and things like that meant that it wasn't the most flexible option, and definitely not the cheapest and probably more expensive one. So you need to have a read through of this to understand those differences, and maybe do your own research if you're interested as well. And then you can come back to answering this question here. So firstly, the first one was stating two features of the von Neumann architecture. So that you could mention things like the registers and buses and things in the von Neumann architecture. Let's take a little look at the model answer down here. By the way, you should try and answer these questions on your own before you watch this. But if you're kind of stuck and you want to get some help, then have a look at what I'm saying now. But we'll continue with it. So yeah, they're saying things in model answers like they will accept acronyms, and they want ALU, CU, and they want to hear about different registers, control unit, ALU, special registers such as data and instruction registers. They're also talking about features that instructions and data are stored in the same area of memory. So as I said, that's a feature of the von Neumann, not the Harvard one. And single sets of buses. So again, knowing the difference between von Neumann and Harvard is important here, because then you know how it's architectured. So after that question, they then come on to one which is we looked at in two previous videos on machine code. So you will not be able to program this, but you have to run through it in your head. Now, the best way you can understand this computer program here is to write out a trace table. Unfortunately, it's quite simple, this one. It's just you just go through ones. It's not looping, which will make it more complicated. And all they're asking you to do is look at this program and decide whether or not, because basically the final output of this program is it outputs either a red, whatever is stored, the number stored for red light, which is 0, and the number stored for green light, which is 1, and depending on an input. So it's going to show a red light or a green light. And if you read through this code, you can see that the if statement, the branch, the condition, BRP except, right? If that is true, it will only be true if what the number you've inputted, if you take that away from the value stored in max, so 5, will that be positive? So basically, we need to think about what number do I need to take off 5 for it to be negative. or not positive. And then you can work out which boxes will tick for these inputs, which boxes will tick for those. So the little demonstration of how you could do a trace table with these kind of programs: write down all the variables, red light, green light, they're not going to change. Max is not going to change, but entry will, depending on what you input. And depending on what you input, that's going to change the result of the BRP evaluation, where we're loading max from the memory, and we're subtracting it from what we input or stored in the entry variable. And then you have to make sure you've got to try and write down what's in the accumulator at any one time. So when you input something into the accumulator, you're going to add 1. And then they're going to load max, so it's going to put that into the accumulator. And then when you take 1 off or entry off from the accumulator, you end up with 4. And then that is greater than 4, so you can say yes. So it's a bit easier way of explicitly writing it out if you need to do that. Now remember, this is only 2 marks because it's a fairly simple program. Once you kind of figured out what it's doing, you should be able to just quickly know which ones you're going to tick and which ones you won't. Next question they ask you about is breaking down the fetch, execute, decode cycle. Basically, they're saying for this line here, load red light, assuming that red light is stored at memory location 11, discuss what's going on in this fetch, execute cycle, what registers are going to be used in buses and things. So when you do load red light. So, for example, the load red light instruction has been fetched and decoded, and now it's going to be executed. So what happens? Well, load red light is pointing to address 11. So I'm going to write this down below. Memory data register has so memory address register has address 11 and sends it down the address bus. You're going to send it down that address bus. We should get a picture of if you need a picture of the CPU, there's one further up here. So we've got this address register, memory address register. It's got this address for this next instruction, which is load red light. It's going to get sent down from the memory address register, going to send down the address bus into memory. Then the data, which is, well, if you look at what is stored in red light, is 0. The data 0, that will then is sent down the data bus and stored in the memory data register. So sent down the data bus stored in the memory data register. And then you could also say, because if you want to be able to do something, you're going to want to subtract entry from that. We're then going to need to copy that into the accumulator. So, and then this is copied into the accumulator. That's the kind of answer they're looking for. But you've fully shown you understand the fetch, execute cycle and how all the different registers are using. And have a look at the mark scheme here and see what they say. It's basically exactly what I said. Next question is, they say, write in code in high-level language or pseudocode has the same functionality. So it's a very simple program. It's an if statement, and essentially, if the number that you input is greater than 5, so then you output red light, else you output green light. If it's less than or equal to 5, you output green light. Yeah. So, and the last question they want you to do is discuss the differences between assembly code and high-level languages. So this is an essay question, you can tell because they've got a star. You need to discuss the advantages and disadvantages of writing programs in assembly code rather than high-level languages. So here, when each approach might be used and why the coffee machine program is programmed in assembly code. So here this is referring back to what I said at the beginning. Why would you use a machine code at all? Because some machines don't have operating systems. A kettle has a circuit board on it and a processor, but there's no specific operating system. So you can't program it in Java or C# or whatever. You have to program it in the machine instructions in the, on that chip. Now, for a small device like that, has simple function like boil the kettle, or the coffee machine, you know, when the water temperature is high enough. It's easy to program something like that. But if with a more complicated program, it's going to be harder. So that you know, you need to have some specialist skills, someone who can understand how to write machine code. It'd be more difficult to debug that. Whereas when you write in a high-level language, you've got a lot more tools that will help you understand when your program's going right or wrong, and you don't have to worry about so much about memory and everything. But with machine-level language, you're directly controlling the memory and the hardware. So you've got to be really sure that you know what you're doing. So machine code is useful, but more complex and difficult to write, perhaps. And when you're discussing this answer, we stick to the question: what are the advantages and disadvantages of that? As I've said a few. And then when might you use each one? Well, you know, you're going to use machine code for like things that don't have operating systems. And then you could say why the coffee machine was programmed to that. Now, if we have a look at the model answer here, it's always good to read these. That's why I put them there. They're always looking for they are looking for, this is on the right here is a breakdown of a really good answer. And on the left here is a description of what they're looking for. So a very high answer: the candidate demonstrates thorough knowledge and understanding of assembly code and high-level languages, right? The material is generally accurate and detailed. You must be able to show how you can apply your knowledge and understand directly and consistently to the context provided. So the context of a kettle or whatever. The candidates provide a thorough discussion which is well balanced. So you want to evaluate, say what's good and what's bad and what you would improve on, and develop a well-developed line of reasoning. And often what they're looking for here, they want your knowledge, your content, what you know about the things. Then they want to show how you would apply it, and then they want to show how you would evaluate it. So go and have a read of these model answers and try and answer these questions yourself. And then have a look at the other one. And also, I will add some more past paper questions at some point if you want. Maybe put some comments below if you do want more. And if you're in my class, you can look at the folder.